Hello and welcome back everyone. Let us begin from where we have left off. In the previous session, we have completed the modeling of the snapfit. In this session, we will create the deck to perform the snapfit simulation. So instead of assembly, let us go for the step, and here we are going to create the two step. From the project description, we know we want to calculate the force required to push the insert into the buckle and pull it out from the buckle. So basically, we are going to perform this analysis in two steps. In first step, we are going to push the insert, and in second step, we are going to pull it out. If you currently notice, in the assembly position, they are in the engage position. In few minutes, we are going to move this insert into the disengage position. As of now, let us first go for the create, and here let us say push. Then I am going to perform the static analysis and simply go for continue. Since here the assembly and the disassembly will happen by virtue of the elasticity, the large deformation is bound to happen. So in the NL geom I am going to switch it on, and under the incrementation parameter let us say 0.1, and for the maximum let us say 0.2. These are the by default parameter that we have been using for this course. If later on we found out that our analysis is highly stable, then we can increase the initial increment and the maximum increment. As of now, let us simply go for the OK. The push step have been created. Now let us create another step, and here I will call it as a pull step. Let us go for the static. Again, let us follow the same procedure. So here I will switch on NL geom, go for the incrementation, and let us put 0.1 and 0.2 in initial increment and maximum increment. Simply go for OK again. Let us close this one and let us go for the assembly. For this particular snapfit simulation, we are going to assume the base position as the disengage position. So let us disengage the insert from the buckle. Simply go for the instance, go for the translate and select the insert. Again, here it is asking me select the instance to translate. So I have already selected. Simply go for done, and let us select the direction vector as a y-axis. And for the distance, let us put it into the particular view first. So I will go for the XY. Let us switch off the perspective. And for the distance, as of now, I don't have any idea. Let us try to put 15. Let us go for continue. Nope, it's not working. Still insert and the buckle are intersecting in this region. So I will go for back. Instead of 15, let us go for 20. Go for continue. With the 20 mm, indeed, the insert and buckle have disengaged, but you can note here there is lot of gap. If you are performing the static analysis, that too when we are planning to create the contact, then it is always better practice to have the two components which are going to be in contact in just touch condition. So here let me again go for back. Instead of 20, let us put 19 and go for done. Now this position looks fairly appropriate. Simply go for OK. And done. Keep in mind, we have moved the insert by 19 mm. Now simply go to the isometric view again, and now let us move ahead. So let us go for the interaction, and now let us think about what we are planning to do. Basically, we want to push this insert into the buckle. There are two ways through which we can do it. First one is, of course, we can just apply the force and push the insert into the buckle, but our objective is to calculate the force itself. Not only that, here we are not sure about how much force it is required to push the insert into the buckle. So, to apply the force as an input does not seem to be appropriate. Instead of that, think about it. We already know that in order to engage the insert into the buckle, this insert has to travel by 19 mm. So what if we apply the displacement itself? Well, of course we can do it. So, we are going to apply the displacement at the top face. And now again think about it. If we are applying the displacement in the top face, this insert is going to move in the downward direction. In this space, it will come in contact with the buckle, and then the force will transfer to the buckle. So for the convergence, this buckle needs some boundary condition. So this bottom face of the buckle we are going to fix in all degrees of freedom. So this cantilever extruded part or jaws can move in and out depending upon engagement and disengagement. Before we create the boundary condition on respective faces, let us create the provision in terms of kinematic coupling. It is always better practice to use the kinematic coupling so that we can request the different output on them. in order to create the kinematic coupling, we need the reference point. So prior to that, let me create 2 points first. Simply select this one, and let us repeat the procedure for the bottom face. Once we have the point, then simply go for the reference point, select this middle point, and again select this middle point. Once the two reference points have been selected, we can go for the constraint. From here, if you want to rename the constraint, you can do it. As of now, I will go ahead. Here I will go for coupling and go for continue. Then here it is asking me to select the constraint control point. So I will go for create set, and let us rename the set as loading point. Then simply go ahead and select this reference point as loading point, and then simply go for done. You can note now here it is asking me to select the constraint region type. So basically I want to constrain this entire surface with respect to this reference point. So I will go for surface. Here I don't want to create the set for the surface, so I will just remove this tick. Simply select this face and go for done. Make sure the kinematic option is on and all degrees of freedom have been ticked. Simply go for OK, and let us repeat the same procedure for the second constraint. For the set, I will say BC set. BC stands for boundary condition over here. Select the reference point, go for done. Then it is asking me to select the surface. Click on surface, remove the set creation tick, select the face and go for done. Make sure kinematic is on and all degrees of freedom have been ticked and go for OK. This way we have created the provision for applying the displacement and applying the boundary condition. Once we apply the displacement at the loading point on the insert, automatically this insert will go in the downward direction and eventually it will come in contact with the buckle. That's why we have to exclusively told the abacus that which surface are going to come in contact. In order to create the contact, we can simply go for create interaction. From here, it is giving me different option to create the contact. As of now, we are performing the Abaqus standard analysis. So here I will go for surface to surface. Let us go for the LH contact. Then under the step, instead of pull, let me create this contact from the beginning itself. So make sure initial have been set, surface to surface have been set, and go for continue. In the status bar, you can note currently it is asking me to select the main surface. Here I will go for create surface, and under the name let me put M01. So basically I want to create the master surface. Here we have the buckle and the insert. Both of these components have the same material, so we can say in terms of material wise the stiffness is same for both the component. But if you check out the geometry, then of course in terms of geometry buckle has the largest dimension and hence it is little bit stiffer as compared to insert. In addition to that, one of the most important parameter over here is the boundary condition. The component or the face which has the boundary condition applied to it should be selected as the master surface. Of course, the bottom face of the buckle have the boundary condition which we are going to fix in all degrees of freedom. So for the master surface, I will go with the buckle. Simply select one surface, press and hold shift button and select the remaining surfaces. Here instead of individual, we can go with biangle option also. Select this one. Let us move it. Press and hold shift and make sure the entire face we have selected. Simply go for done. Now it is asking me to choose the secondary type. So again surface I will go for. Here I will go with slave 01. And then select this one, then select this one. Make sure every single thing have been selected and simply go for done. So this way we have created the main surface as master surface, secondary surface which is the slave surface. Sliding formulation I will keep it to the default one only, and under the contact interaction property let us create the interaction property from here. Simply go for type friction, then let us go for contact and go for continue. Under the mechanical, in order to apply the friction, let us go for tangential behavior. Instead of frictionless, let us go for penalty, friction coefficient to be 0.2, and let us go for normal behavior to be hard contact. Once that is done, simply hit OK. Now again let us go for OK. Now similar to this contact, let us repeat the procedure to create the contact on the right side. Once all the interaction have been created, let us move ahead and create the loads. Under the load, on this particular node, we are going to apply the downward displacement in the y direction with the displacement value of -19 mm. To apply the displacement, simply go for boundary condition. Instead of initial, let me first change the name. So here I will go for displacement and let us go for 19 mm. Under the step, instead of initial, let us select the push. Under the push, let us go for the displacement and go for continue. So here it is asking me to select the region for the boundary condition. Instead of creating the set, I have already created the set of loading point onto which we are planning to apply the displacement. You can click on the highlight selection in the viewport and verify the node. Simply go for continue and let us tick the U2 because you can note Y is the direction in which we want to apply the displacement. So here I will go for -19. Here take some time and think about it. Our objective is just to push the inset into the buckle. If we apply the boundary condition in Y direction, definitely that is going to happen. But what about this rest of the degrees of freedom? As of now, by not ticking into these degrees of freedom, basically we are seeing that this insert can move in any direction, be it X and Z. Practically, we know that that is not going to happen. So of course, it makes sense to constrain these degrees of freedom. But if you are beginner, many times you will doubt this boundary condition. So as of now, let me keep these degrees of freedom as free only, and you will see that we will get into some numerical singularity because of this boundary condition. So let us go for OK, and again let us go for boundary condition. Just now, under the push step, we have displaced this insert into the buckle. Now in the second step, we want to move this insert from the buckle. So instead of push, I will simply go for pull. Again go for the displacement and rotation and go for continue. Again go for loading point and go for continue, and under U2 basically I will say 0 because this will be treated as a reference state. In the first step, from the reference state, that is from 0, 0, 0, this particular point has moved in the downward direction by 19 mm. So in the second step, if I again go for the 0, then this reference point, which will be somewhere over here at the end of the push step, will have to go to the top again. So of course you can do this particular thing, but instead of creating the separate boundary condition, we can modify the existing boundary condition also. So simply go for cancel. Let us say no, I don't want to save the changes. Go for boundary manager, and you can note I have created the displacement of 19 mm in the push step, and in the pull step that same displacement have been propagated. Instead of having the same displacement in the pull step, simply click on this propagated step, go for edit, and under -19 simply put 0. You can note the star has appeared over here indicating that this step have been modified. Simply go for OK, and now close this one. Once this is done, let us apply the boundary condition to fix the bottom face. That particular boundary condition I will put it in the initial step, and let us call this as a fixed BC, or let's say fixed face. Make sure the step have been selected as the initial. Go for symmetry and in custard and go for continue. From here, let us go with the BC set and go for continue. Go with the in custard and go for OK. Now again let us go for boundary manager, and you will note even if we have created the boundary condition in the initial step, automatically the same boundary condition will get propagated for the rest of the step. Once this is clear, simply go for close, and now let us move ahead and mesh the component. So I will go for the mesh. Let us click on the part. Here I will go for the element type. Let us remove this reduce integration element, and let us mesh, or let us first seed the part. For this particular exercise, let us go with the element size of 1 mm and go for OK. As of now, I am assuming that I have done the mesh conversion study. 1 mm is the optimum size for this component. Let us go with the mesh part and simply go for yes. Mesh looks appropriate with this. Again, let us go for the insert. Let us say element type, reduce integration remove, seed the part. Follow the same step basically. Once the meshing have been done, let us quickly check the output parameter that we have requested. Simply go for the step, go for the output. Simply click on the edit button and you can note, currently I have requested the stresses, strain, displacement, forces and reaction. So in terms of field output, everything have been covered. Simply go for OK and close this one. Let us go for the history output, go for the push and go for the edit. Over here, you can note all the energies have been requested. Since we are performing the static analysis, here we don't require the energies. But still, I will keep them. But in addition to that, I want to request the reaction forces on the particular set. So here I will go for the set. Let us go with the loading point. And instead of energies, let us go for the forces. Go with the RF. And here, let us try to request the displacement also. So let me go for the displacement and go for the U. Once these two things have been ticked, simply go for the OK and let us close this one. In addition to this, I am also going to request one additional output. Basically, during the analysis, I want to check the displacement of this loading point. If you remember, in order to do that, we can simply monitor this node. To monitor this node, we can go for model, go for edit keyword and go for the snapfit. Let us scroll downward. Let me try to maximize this one. Then let us scroll upward. So this is our step number 1, the push step. Scroll downward and here you can see star output history. So just below that, let me type star monitor, comma, node is equal to, or let us first say degree of freedom. Here I want to monitor the y direction, so I will say DOF equal to 2, comma, node equal to. In front of node equal to, I need to put the set name. That particular set name is the loading point. So simply I will copy this loading point set, paste it over here and simply go for OK. Once everything have been set, we will create the job. Prior to that, just keep in mind, on this loading point, we only have one boundary condition where we are displacing this node in the downward direction and rest of the degrees of freedom are free. Based upon our previous experience, this boundary condition might create a problem. So essentially, we will have to monitor the run and check that this particular boundary condition is not causing the problem. Let us go for the job now. Go for job manager and go for create. Here I will type snapfit. Let us go for TR1. Simply go for continue. Under the parallelization, since I am using multiple core processor, I will go for 8. Go for OK and simply submit the job. We will continue this project in the next session. Till then, take care, goodbye.